Hi guys, today we got to talk about two things. The first one's called the intermediate value theorem, and it's one of those kind of theorems that I look at and I think, well, that was pretty obvious, but we write it down because in calculus we're going to eventually use it. It's another one that we use to prove things later on in calculus. So here's what it says. I got some function. There's my pretty function. And on this function I have this point here. I'm going to call this f of a. So some y value, and then I have another y value, f of b. And what they're saying in the intermediate value theorem, it says, and you're reading this before this video, so you've kind of already noticed this, it says if f of x is continuous, which mine is, it's continuous, no holes, no asymptotes, and k is between f of a and f of b, so somewhere in here you have a k value, let's just call it right here, we'll call this value k, then there must be, so if k is in between these two, there has to be some place, which would be right here, and we'll call this c, there has to be some x value to go with that k value, so that f of c equals k. So the function evaluated at c equals k. How do we use it? Well, for what we're going to use it for, one way is if we have a function that's f of x equals x cubed minus 3x minus 2. And I'm going to look at that on the interval between 0 and 1. Okay, that's not an ordered pair. I'm using set notation. So between 0 and 1 on the number line is what I'm doing there. That's set notation. Alright, so what we can do is if I plug in 0, I get negative 2. And if I plug in 1, I think I just lied there. Let's make this a plus. Sorry, go back up, change this, my fault. Alright, so if I plug in 0, I still get negative 2. But if I plug in 1, I get 1 plus 3, which is 4, minus 2, which is a positive 2. Which just told me that at 0 I was at negative 2, and at 1 I'm at positive 2, which means my function does something in here. Which proved to me, or verified if you want to say, because I went from a negative down here to a positive, I had to cross the x-axis. So I verified that a 0 existed somewhere between 0 and 1, right? Because if I go from a positive to a negative or negative to a positive, I'm crossing the x-axis. So there had to be a 0. Okay, when they say 0, they're talking about an x-intercept. And that's the pretty easy way of the intermediate value theorem. They're saying that this is the 0 is the k value, and the point that it happens would be c. Okay? The other thing that we can do with it is, let's say I have this function here, f of x equals x squared minus 6x plus 8. And we're going to look at it on the interval between 0 and 3. We're going to see somewhere on this interval between 0 and 3, does the function f of c equal 0? Can you tell me where that happens? So basically we want to find the c value. Where does this function equal 0? So I set that up, x squared minus 6x plus 8. Well, we want the function itself to equal 0. Looks like an algebra 2 problem to me. So I get x minus 2 and x minus 4. And my answers are 2 and 4. The only problem is I want on this interval, and so 4 is out. So the answer would be c equals 2. Okay, that's the intermediate value theorem. It's a theorem that you'll see. It's not a difficult theorem, but it's just one to be aware of. You might have reference to it. The second thing we're going to talk about today, because that one was really easy, is a vertical asymptote. And I'm putting them together because I believe that most of you know how to find a vertical asymptote. If f of x equals 2 over x minus 3, the vertical asymptote happens at x equals positive 3. Vertical asymptotes happen where the denominator is 0. When I draw them, I like to put like a little dotted line there. You don't even have to graph for what we're doing today. What you have to do is just tell me where they happen. Okay, so let's say f of x equals 2 plus x over x squared times the quantity of 1 minus x. This one actually has two vertical asymptotes because if I look at the denominator, nothing cancels with the numerator. So that means I can just look at the denominator. I would have a vertical asymptote at x equals 0 and at x equals 1, right? Because if I set this equal to 0, 0 and 1. All right, let's try another one. What about if you have 2x minus 1 over 3x squared minus 6x minus 24? Well, first of all, looking at that after I wrote it, I would change this to 2x minus 1 over x squared minus 2x minus 8 and go from there. And if I factor that, I get x minus 4 and x plus 2. Does anything cancel? Nothing cancels, so then my vertical asymptotes would be at x equals 4 and x equals negative 2. Why do I keep wondering if stuff cancels? Well, not always is there a vertical asymptote. For example, if f of x equals x squared minus 6x minus 7 over x plus 1, it looks like we might have a vertical asymptote at negative 1. But in reality, if I factor the numerator, I get x plus 1 times x minus 7. And down here I get x plus 1. These cancel. So that means there's a hole at x equals negative 1, which is what we talked about is removable discontinuity. And there's no longer a vertical asymptote, meaning there would be a limit because it's removable. All right, have a good day.